So I'll wrap up the introduction. Sorry for the interruption. After the first two talks by Axel and Andrea, I'll go more in depth towards the principles of computed tomography and the technical design of beads. So this is a layout of the building of SESAME. This is the north side where beads will be installed. And as you can see, we will use one of the longest straight sections that are available in the building. Beads will be installed on a straight section of the ring, and it will be 45 meters long to exploit long propagation distance, so to look at our source from as far as possible. We will quickly see why this is important. This is a general layout of the beamline. It is divided in 4 parts. From the left, there is a part called front end inside the storage ring of the accelerator. There is then a small optics hatch where optical components are hosted. And then there is a long shielded pipe bringing the X-ray to another shielded hatch where the experiment takes place, which is the BIT experimental hatch. And this is also a layout of the beamline, more let's say a functional layout. We have again the wall of the SESAME storage ring here in the middle. What is on the left is inside the tunnel, so it's something that as users you probably won't see. It's called front end. We have a fixed mask, we have primary slits and filters to tailor the size and the properties of the beam. DMM stands for double multilayer monochromator, which is a system of 2 crystals reflecting the beam for energy selection. And then on the right, from 33 to 45 meters from source, we have our experiment. So from this layout, you can already see that the beamline has been designed to allow 2 different modes of operation. There is what is illustrated as pink is our white beam or pink beam option when the mirrors of the monochromator are out of the way, so we allow the full flux to travel to the experiment. This is for a high speed and high flux experiment, large dense samples, for example. When we want energy resolution, we insert the monochromator and we work with one single energy, so monochromatic beam for energy resolution and more experiments requiring a higher like an energy selection. The source of the beamline, this has been introduced by my colleague Axel already. Just a few words. It was decided already in 2019 to go for a wavelength shifter or superband concept. The decision for a 3-pole wiggler was taken in September last year. The reason is explained in this slide. So this is a simulation of the photon flux we obtained with a 3-pole wiggler, such a device, a 3 Tesla 3-pole wiggler. The comparison, BT is in orange in this plot. The comparison is done with the beamlines that are sitting on a bending magnet. So you can see that we can exploit a much broader spectrum, particularly with the photon energies that are not limited to 20 or 30 kiloelectron volt, but we can go up to 50 kiloelectron volt. This has a direct impact on the scientific case because it allows us to access higher energies, allow us to access a broader variety of samples, more dense and larger samples. Now, very quickly on the principles of computed tomography. This is the first CT scanner that was introduced in a hospital in the UK in 1971. So CT, computed tomography, was introduced in the clinics for imaging of the human body. How a beamline for tomography at a modern synchrotron facility looks like is actually very different. This is a picture of Tomcat at the Swiss Light Source, where I'm sitting now for a training. This is the experimental hatch of Tomcat. So we have the beam entering from the left side of the figure. The X-rays are traveling here in the middle of the figure through the sample, which is positioned on a rotation stage, so the sample can rotate. And then they are intercepted by a microscope, which is sitting here behind the sample. From this diagram, we see what happens. The X-rays are passing through the sample, and they are intercepted by a scintillator, by a thin foil, scintillating foil, which converts the X-ray to visible light. The visible light is then magnified by a microscope objective eventually, and then hits the screen of a detector, a CCD. In this diagram, it will be a CMOS detector in our case. This procedure is applied for all possible angles, 180 or 360 degrees, depending on the scan. And the result for each row of the detector is a figure like this. This is called sinogram, which is the detector response for all 180 degrees of orientation. These images are then processed by a computer that does the tomographic reconstruction, applies the radon transform, and from this we obtain slices and a pack of slices, in fact, which give us the 3D geometry, internal geometry of the sample. One of the techniques that we would like to apply at BEATS, and this is why tomography at a synchrotron facility becomes very interesting, is the possibility to enhance the contrast of light elements thanks to phase contrast. So this diagram from a book from Phil Wilmot explains how phase contrast is achieved. From the left, we have the X-rays. They are hitting some disks of different materials. You see that we have only 2 disks that are dark, so they are dense, and the rest are 1, 2, 3, 4, 5 disks of that are transparent, so very light materials that do not attenuate the X-ray. So when we put the detector right after these disks, you see that we have high contrast only for the 2 dense materials, whereas for the rest, we hardly see the shadow of the transparent disks. However, when we let light propagate further by taking the detector further away from the image plane, further away from the disks, we have that the edges of the materials are enhanced to Fresnel diffraction of those edges. When we bring the detector too far, we enter a Fraunhofer diffraction regime where we do not distinguish the shape anymore of the original object, only an interference pattern. So what we do in tomography is to stay in this regime, in the Fresnel regime, and enhance the edges of our objects by letting the X-ray propagate after passing through the sample. And this is actually the result of this technique and how it can be applied. This is a zebrafish embryo, so a 3D object which is composed of very light materials with atomic density very close to that of water, in fact. And you see that in the radiographic images, in the projections, which is the first row of this image, we barely see something. What we see is actually only these 2 little dark spots, which are the ear stones. So these are the only dense parts of the sample. The second and the third row are 3D reconstructions. So these are already slices through 3D volumes. The second row is a reconstruction done in absorption. The third row is a reconstruction done with phase retrieval. So you see that going from the left to the right, when we increase the propagation distance from the second row, we enhance the edges of the different phases of the embryo. When we applied phase reconstruction, so phase retrieval, we're not sensitive anymore to the attenuation of the X-ray, but to the phase shift due to the passage of X-rays through different phases of the sample. And we can boost very much the contrast of different parts of the embryo. Now, one of the conditions to apply phase retrieval and to enhance these edges is to have sharp edges. And this is something we all have, how to say, a common experience of from when you look at the shadow of your hand as illuminated by the sun or by a light bulb. You know that the edges are more or less sharp, the edges of that shadow, depending on the relative size between the source of illumination, object, and detector, or the wall where you project the shadow, but also depend on the size of the source. So we need a very small source, or as small as possible source, to have a sharp edge without blurring of the edge. And the source size, the synchrotron facility mainly depends on the properties of the storage ring. So how well you can confine the electrons in the ring while they circulate. For beads, the distance from source is comparable to that of other beamlines for tomography, but the X-ray source is not. So we have to act on this. And the way we will do, if we look again at the layout of the beamline, is by introducing slits in the front end, which is just an aperture that we can close to tailor the effective source size. So we create a secondary source with a reduced size down to 0.5 millimeter, through which we can look at samples and apply phase contrast. So going back to the possible modalities of operation, we have now a mode 1, let's say, white beam, and mode 2, monochromatic beam for experiments requiring high flux or energy sensitivity. But we can then operate also using absorption, so with high flux, slits open, or for high sensitivity and phase contrast by closing the primary slits and creating a secondary source with a small size. Very quickly, the equipment of the beamline, which is what we are designing and procuring right now. The front end is, as I mentioned, is there to safeguard the experiment, to define the beam size and properties. So we have SESAME and Electra right now designing the fixed mask, for example. This is the aperture that defines how much the fan of radiation that is allowed through the beamline. We have ALBA and ESRF together with SESAME designing the hatches for the optics and for the experiment. And then we have the ESRF helping on the design of attenuator systems and of the primary slits. For example, this is a picture from the slits of ID19. We will have the pleasure and the honor at Beats to install the recently exchanged and refurbished ID19 slits of the SRF. So back to the layout. This is a slide on the double multilayer monochromator. It's a picture from Tomcat, which is inspiring our design. This is a system with 2 crystals, 1 and 2, where the beam is reflected to select an energy between 8 and 50 kiloelectron volt. The way it works is that by changing the angle at which the beam is reflected, one can select, thanks to Bragg's law, an energy in this range, 80 to 50 kiloelectron volts. So the 2 crystals are moving in space up to 1 to 2 meters of excursion. Once we reach the experimental hatch, which is the part that you will visit as users, hopefully, we have a first system of slits and alignment provisions to align the sample in the beam. We then have a pipe bringing the beam again to the sample position, where we have a tomographic sample stage, and then a table with microscopes and a beam stop. The size of the beam for the experiment can be changed by bringing the sample up and down the hatch. So you see that from around 40 millimeters of beam at the entrance of the hatch, we can exploit up to 50. We are trying to bring this to 70 millimeters at the end of the hatch, so to illuminate larger samples. The sample stage is a device from which our colleagues at the SRF have a lot of experience. Is a high precision and heavy duty sample stage. You see here two images from the SRF, from BM5 and ID19 at the SRF. The important thing here is that it must be the system must be very rigid and allow us to prepare stack of samples like this to automate, like the one you see here on the bottom right, to automate the scanning of a series of samples without interrupting the procedure and entering again the hatch. We then have a detector stage, which is again inspired by a solution from the SRF. On the right is the detector stage of ID15 we are inspiring from. And on the left, the mechanical design of the detector stage that we are actually developing. As you see, it can host two detectors for different magnifications. So there is a high resolution detector on the left with two different objectives, and the lower magnification one on the right. And the cameras are two identical cameras, also very well established and proved at the SRF, which are scientific CMOS cameras. So with this portfolio of detectors, we will be able to provide different magnifications. So different magnifications means different resolutions at which we can scan, and also different field of view, so sizes of samples that we can possibly see. And from 1-fold to 10-fold magnification, which is what we aim at installing, you can see that we will go from large samples up to 15 millimeters in size with a pixel size of 6 micron, 6.5, down to samples of 1 or 2 millimeters with the sub-micron resolution, which gives us a rather versatile portfolio of detectors that can be used in combination. Finally, some words on how we can actually perform in situ studies. So we are considering the installation of a mechanical rig for mechanical tests. This is an example from the APS, I believe. It's a simple system that allows to compress and pull samples. This is very interesting, for example, for the analysis of biological samples under mechanical load, but also plastic foams or other polymers, how they deform during load, or for example, 3D printed materials or lightweight materials like metal foams and so forth. Another sample environment is a furnace for in situ heating. This is an example we are trying to replicate from the SRF. Is a furnace that can go up to 1500 degrees Celsius and can be used to study, for example, the evolution and phase transition of composite materials during heating. Generally, at this part of the presentation, one would explain what the tremendous infrastructure for data acquisition and data processing behind such experiment would look like. But for this, we will have, we are lucky, we will have a specific talk tomorrow morning at 10 from my colleague, Dr. Charalambos Chrysostomou, who is the leader of the work package 7 of BEATS, dedicated to the design and the installation of computing infrastructure for data acquisition, processing, and storage. So don't miss the talk tomorrow by Dr. Chrysostomou. Without spoiling that talk, what I want to mention, and I conclude here, is that we will provide the users with a set of software, mainly open source, for 3D data analysis and processing. One very interesting thing that can be generated with high resolution and high quality 3D data is numerical simulations for solid mechanics or fluid or gas dynamics, for example. This is the plot. The figure shows an example from a bone sample that was scanned with the synchrotron CT. It was first of all segmented and prepared to simulate the response of this tissue under mechanical compression. So this is where the user, the role of the user becomes very important. If you have a particular expertise, a particular requirement, we would be happy to collaborate to establish a pipeline for the generation of such numerical simulations, and we hope we can collaborate in the next years. So I think the next talk from Alexander Rack, from Dr. Rack, will cover all the potential scientific application of this experiment. And with this, I would like to thank you, and sorry for the initial complications.
Thank you very much indeed, Dr. Iori. It's really a pleasure to hear from you in terms of the progress, the design of the Beamline, and we're very happy that the initial hiccups and so on could be sorted out. Apologies also for some technical issues. I understand that there was some echo during the presentation, so we apologize for that. We are looking into it just to make sure that it does not appear again. But nevertheless, I hope that you were able to hear the presentation content. Are there any questions to Gianluca at this point?
Yes, I would like to ask a question.
Do we have any questions on the chat? Do go.
Yes, thank you. I want to ask you regarding the payload of the moving stage and
Yes.
the accuracy of the movement for the stage and the range for the z-axis, and also for the rotating, the accuracy of the rotation and the speed of the rotation for the moving stage.
Yeah, so the speed and the accuracy are a compromise with the resolution that we want to achieve. So the resolution in terms of imaging will be around 1 micron or sub-micron, which is also the resolution we have to achieve with the rotating stage in order to have an image free from movement artifacts. Or the vertical stroke is half meter in this design. So it's as you saw in the picture where there was this piled stack of rocks, it can be actually very tall, the sample size. We can scan a taller sample by performing a stack of scans. The payload. there are the factory, the supplier we are discussing with provides different versions. I hope we can have a limit around 25 kilograms. So quite stable and stiff in order to also mount sample stages on top. Yeah, in situ stages on top.
And also, I want to ask you regarding the rotation speed and the
yes.
accuracy.
So it's up to actually 1 hertz. So as you know, then comes the limitation in terms of how fast we can image, because we cannot do one tomography scan in 1 second with the detectors we have. The detectors are limited to 100 frames per second when you acquire with a full frame, which means that to acquire 1,000 or 2,000 projections, you will never perform one rotation in less than 10 seconds, 20 seconds, right? So the scan speed and rotation speed is very much function of how dense the sample is, if you illuminate it with the full white beam or a monochromatic beam and so forth.
I also want to ask you, for the beamline, is it only monochromator, or you can like adjust the setting, for example, to use pink beam tomography?
No,
like
pink beam is beam is the first thing we will. I'm sorry if you couldn't hear well the presentation. Pink beam is possible.
Thank you very much.
Yeah, thank you for the questions.